Risk management principles and procedure, proactive hazard identification, structured risk evaluation, and integrated decision-making in oil and gas projects. Risk management in engineering design, particularly within the oil and gas industry, is not a safety formality. It is the architecture of operational resilience. Like meeting minutes that transform discussion into execution, effective risk management translates anticipation into action. It protects not only lives and assets, but also timelines, reputations, and long-term viability. At its core, risk management must be both systematic and cyclical, never static. It begins by identifying known and potential hazards, not just at the project level, but embedded within operational behavior, design assumptions, equipment configurations, and process interfaces. Every activity, whether a design choice, procurement strategy, or procedural protocol, must be filtered through a structured hazard lens. What could go wrong? How might it escalate? What would it impact? To be effective, this approach must include comprehensive hazard identification. Start by isolating all potentially hazardous activities, not only those linked to direct process operations, but those that emerge during transitions, commissioning, decommissioning, modifications, or change of use. Structured risk evaluation. Every identified hazard should be assessed for its consequence and probability. Cost-effective prioritization is essential, focusing first on what could lead to injury, environmental harm, or catastrophic loss. Embedded design controls. Risk is most effectively managed when addressed upstream. Engineering reviews must ensure that design incorporates fail-safes, materials selection, spacing, and layout that minimize vulnerability. Waiting until construction or operation to control risks is always more expensive and less effective. Lifecycle coverage. Design risk reviews must also extend to acquisitions, asset disposal, and decommissioning, where residual energy, chemical contamination, or structural decay can pose overlooked dangers. From first sketch to final dismantling, the hazard lens must remain focused. Structured risk management cycle. A disciplined process should follow 4 essential steps. 1. Identify hazards. 2. Evaluate and analyze the risk. 3. Implement controls to manage the risk. And 4. Review and verify the outcome. This cycle must be continuous, reviewed regularly, and responsive to change. When this structured approach is ignored or handled informally, the project inherits hidden costs. Scope creep due to overlooked risks, late-stage redesigns, schedule delays, and worst of all, incidents that could have been predicted and prevented. Risk management is not about achieving perfection or eliminating all uncertainty. It is about knowing the landscape well enough to move decisively, design confidently, and act responsibly. Like well-circulated meeting minutes, it ensures alignment across teams, disciplines, and decision points, so that risks are not revisited as surprises, but managed as part of the project DNA. In oil and gas engineering, where the stakes are high and complexity is inherent, effective risk management is the keystone of successful project delivery. It is not a checklist. It is a culture. Risk management principles and procedure. Demonstrating ALARP, balancing risk reduction with practicality and justifiability. In engineering design for oil and gas projects, there are scenarios where hazards cannot be completely eliminated. When elimination isn't feasible due to physical constraints, technological limits, or operational necessity, the question becomes, how much risk is acceptable? This is where the principle of ALARP, as low as reasonably practicable, comes into play. It is not a vague aspiration. It is a disciplined standard that requires deliberate justification. ALARP demands that risk be reduced to the point where any further reduction would be grossly disproportionate to the cost, effort, or time required. In practice, demonstrating ALARP involves objective risk evaluation. Risk levels must be quantified or qualified using established methodologies. This includes assessing the likelihood of the hazard and the severity of its impact on personnel, environment, assets, or operations. Systematic comparison of options. If further reduction is possible, decision makers must weigh the benefit of that additional reduction against its cost. Would spending an additional amount on a more robust containment system save a statistically negligible amount of risk? Would modifying layout or operating protocol significantly reduce hazard exposure for personnel? ALARP requires these trade-offs to be transparent and defensible. Proportionality as a guiding principle. ALARP is not about minimum compliance. It is about responsible engineering. Disproportion does not mean any cost is too high. Rather, it recognizes that there is a point beyond which effort does not meaningfully enhance safety. At the same time, ALARP does not permit inaction where risk reduction is clearly achievable with moderate and proportionate cost. Traceable decision-making. Every decision to accept a risk under ALARP must be traceable. Documentation should include the nature of the hazard, the current controls in place, the options considered for further risk reduction, the reasons for rejecting or accepting them, and the engineering, cost, or scheduling rationale behind those decisions. Independent and informed review, demonstrating ALARP gains credibility when assessments are reviewed independently or involve cross-functional input, design, operations, safety, and maintenance, especially where risk levels are near the boundary of tolerability. LRP is not static. What is considered reasonably practicable today may not be tomorrow. As technologies improve or as incidents elsewhere provide new lessons, projects must reevaluate prior LRP justifications. Continuous improvement is embedded in the LRP ethos. Clarity in risk regions. Risk levels should be classified in 3 zones. Unacceptable region. Risk is intolerable, must be reduced or the activity prohibited. LRP region. Risk is tolerable only if further reduction is impracticable or disproportionate. Broadly acceptable region. Risk is so low that no further action is required beyond standard controls. The responsibility of an engineering team is to ensure that ALARP is not used as a convenient escape from deeper risk reduction, but as a framework that guides serious, justifiable decisions. Ultimately, demonstrating ALARP means being able to stand behind your design, your analysis, and your judgment, with facts, comparisons, and documented reasoning. It is not a safety loophole, it is a standard of excellence. Risk management principles and procedure. Operational risk. Managing change with structured discipline and scalable assessment. In the oil and gas industry, operational risk is not confined to major capital projects or catastrophic events. It often hides within routine facility changes, minor modifications, and day-to-day adjustments. But even the smallest change can ripple through a system and result in significant consequences if not risk assessed properly. Every modification, whether swapping a valve, altering a process line, updating control software, or rerouting equipment, alters the system's behavior. Operational risk management ensures that these changes are intentional, evaluated, and controlled. The fundamental principle: no facility change is too small to escape scrutiny. Each adjustment must go through a proportionate level of risk assessment, scaled to the size and complexity of the change, but never skipped. Key practices in managing operational risk include mandatory risk assessment for all changes. Every facility change, regardless of its size or perceived simplicity, must undergo a formal risk evaluation. This assessment should be embedded into the change management workflow and completed before any physical work begins. Integration with facility change procedures. Operational risk management is not a standalone process. It must be hardwired into facility change protocols. Every engineering modification, maintenance deviation, or procedural update should trigger a structured hazard review using consistent templates and checklists. Use of preliminary screening tools. Screening tools should quickly filter changes based on potential impact, allowing higher risk activities to be flagged early. These tools help avoid overburdening teams with unnecessary deep dives, but ensure that no risk goes unchecked. Application of process hazard analysis, PHA. For moderate to high impact changes, a full process hazard analysis is required. The PHA ensures that potential failure modes, escalation scenarios, and control gaps are identified before implementation. Documentation and traceability. The assessment, findings, and mitigation actions must be documented in a manner that is auditable and transparent. This builds institutional memory and allows future engineers to understand the rationale behind changes. Risk ownership and accountability. Operational risk cannot be outsourced. The initiating engineer, discipline authority, or asset owner must retain responsibility for ensuring that all hazards introduced by the change are identified, mitigated, and communicated. Separation of modifications from projects. Operational risk procedures are tailored for modifications and operational tweaks, not major capital projects. Projects have their own lifecycle and risk protocols. Clarity between these domains avoids gaps and duplication. Continuous monitoring post-change. Managing operational risk does not end with implementation. Changes should be reviewed post-commissioning to validate assumptions, confirm control effectiveness, and capture lessons learned. When operational risks are neglected or superficially assessed, the result is often invisible debt, failures waiting to manifest. Delayed alarms, unexpected shutdowns, or non-compliant emissions may trace back to a poorly evaluated valve swap or undocumented rerouting. Operational risk management is not about saying no to change. It is about saying yes with awareness. It empowers teams to act decisively with safety and system integrity as their compass. In fast-moving facilities where uptime matters, operational risk assessments provide the pause that protects. When practiced well, they transform every change from a vulnerability into an opportunity for disciplined improvement. Risk management principles and procedure. Project risks, designing for uncertainty, structuring for integration. In oil and gas engineering, projects are rarely isolated technical tasks. They are cross-disciplinary, high-stakes ventures that interface with operations, construction, regulatory compliance, environmental exposure, and third-party dependencies. Project risks are broader in scope, more interconnected in impact, and often harder to predict than operational risks. Where operational changes typically involve localized modifications, projects involve systemic transformation. With multiple parties, phases, and interfaces, the risk profile of a project extends beyond safety. It includes cost overruns, delays, flawed designs, misaligned stakeholder expectations, and long-term performance compromises. To manage project risk effectively, the following principles must be embedded into the project development cycle from inception to handover. Begin risk assessments at conceptual stage. Risk management cannot be deferred. By the time detailed design begins, many critical decisions are already locked in. Early-stage assessments during conceptual and feasibility phases are essential to identify design risks, interface mismatches, constructability challenges, and operational bottlenecks. Apply HSE risk requirement screening. Every new project must undergo a structured health, safety, and environmental risk requirement assessment. This determines whether the project warrants a full environmental or safety impact assessment, or whether existing frameworks and controls are sufficient. Use a phased risk approach. As a project evolves, risk must be reassessed at each milestone: conceptual, FEED, detailed design, procurement, construction, commissioning, and decommissioning. Each phase reveals new hazards and dependencies. Risk assessments must be iterative, not one-time events. Include all stakeholders in risk mapping. Project risks are rarely confined to the design team. Operations, maintenance, safety, logistics, and contractors all bring insight into potential hazards. A multidisciplinary team ensures that risks are seen from every angle and that blind spots are minimized. Integrate process hazard analysis, PHA, into early design. PHA should not wait until detailed design. Introducing it during front-end engineering ensures that major risk contributors, such as layout flaws, material incompatibilities, or maintenance inaccessibility, are addressed before they become embedded. Define project-specific risk studies. Not all projects require the same risk toolkit. Depending on complexity, location, and scale, a project may need quantitative risk assessment, QRA, HAZOP, EERA, or safety integrity level studies. These must be defined early and executed at the appropriate phase. Plan for external interfaces. Project risk expands significantly when third parties are involved: suppliers, contractors, joint venture partners, regulators. Interface management and clear responsibility allocation are critical to ensure that risks aren't dropped between organizational boundaries. Use flow diagrams to structure risk management. A clear risk assessment flow diagram ensures that each step, from identifying hazards to verifying mitigations, is mapped, owned, and timed correctly within the project lifecycle. This enforces discipline and transparency. Scale the assessment to the project's impact. Minor brownfield modifications may not need full HSEIA or exhaustive modeling, but greenfield facilities, FPSOs, or refinery modules demand rigorous scrutiny. The scope of risk assessment must match the scale, exposure, and consequence of the project. Projects that skip early risk reviews often suffer from costly rework, late-stage design changes, and operational surprises post-handover. Conversely, Projects that embed risk thinking from day one are more agile, efficient, and resilient, able to anticipate obstacles and engineer them out before they materialize. Project risk management is not just about avoiding failure. It is about designing success. When done right, it ensures that what gets built on paper performs safely, reliably, and sustainably in the real world. It transforms complexity into clarity and aligns every stakeholder toward a common, controlled objective. Risk management principles and procedure criteria for risk tolerability, defining boundaries between acceptance, action, and accountability. In the oil and gas engineering environment, where decisions influence human safety, environmental integrity, and asset reliability, risk tolerability is not a matter of opinion or instinct. It is a structured framework that defines which risks are acceptable, which require further mitigation, and which are fundamentally unacceptable under any circumstance. The concept of risk tolerability anchors all risk-related decisions to clearly defined benchmarks. These benchmarks provide a transparent, justifiable basis for deciding whether a particular hazard can be accepted, needs additional control, or must be eliminated entirely. To operationalize this, the following principles must be embedded into the project and operational risk framework. Establish defined risk thresholds. Risks must be classified into zones: unacceptable, tolerable, with ALARP justification, or broadly acceptable. These zones are not arbitrary. They are derived from internal corporate risk policies, industry norms, and regulatory expectations. Without this structure, teams are left to make subjective judgments, leading to inconsistency and exposure. Separate individual and societal risk criteria. Tolerability criteria must address two dimensions: individual risk, the probability of harm to a single person, typically an employee or contractor, over a defined period, e.g., fatality risk per year. Societal risk, the likelihood of events resulting in multiple fatalities or injuries, relevant in densely occupied platforms, gas processing plants, or urban pipeline corridors. Use risk matrices and quantitative criteria. Consistently, whether qualitative, e.g. low, medium, extreme, or quantitative, e.g. 1 in 1,000 fatality risk per year, the chosen method must be consistently applied across all risk assessments. This allows for prioritization, benchmarking, and transparent decision-making. Ensure risk is evaluated in context. A risk may be technically tolerable by probability, but context matters. If public perception, environmental sensitivity, or regulatory visibility is high, even a tolerable risk might require additional safeguards. Tolerability must not override prudence. Document risk acceptance. Clearly, when a risk is deemed tolerable, whether inherently or through ALARP justification, it must be documented with supporting rationale. This includes the risk level, potential consequences, control measures in place, and reasons why additional reduction is deemed disproportionate. Apply tolerability criteria across the project lifecycle. Risk tolerability is not a one-time evaluation. As projects move from concept through FEED, detailed design, construction, and operation, previously tolerable risks must be re-evaluated against updated conditions, new data, or changed assumptions. Link tolerability to escalation protocols. Risks nearing or exceeding tolerability thresholds should automatically trigger reviews by senior engineering, safety, or executive stakeholders. This escalation ensures that decisions about marginal risks are not made in isolation. Avoid misinterpretation of tolerable risk. Tolerable does not mean safe enough forever. It means the risk in that context and at that time is acceptable, provided all feasible mitigations have been explored. Teams must resist the temptation to treat tolerability as a ceiling of comfort rather than a floor of compliance. Ultimately, risk tolerability criteria provide the moral and technical compass by which risk-based decisions are judged. They offer clarity when trade-offs are complex, urgency when risk is high, and assurance when accountability is needed. By defining what is unacceptable, what is conditionally acceptable, and what is broadly safe, tolerability criteria ensure that projects do not drift into risk tolerance by default, but are guided there by discipline, rigor, and responsible engineering judgment. Risk management principles and procedure. Individual risk criteria, IR, personalizing safety through quantifiable exposure thresholds. While projects often measure risk in collective terms, cost, schedule, system failure, the most meaningful and measurable dimension is individual exposure. Individual risk criteria, IR, focus on the probability of fatality or serious harm to a single person per year, whether they are an employee, contractor, or member of the public. It is the most direct and ethically grounded way to assess whether a risk is truly tolerable. In the oil and gas sector, where proximity to high-pressure systems, volatile chemicals, and complex machinery is common, quantifying individual risk provides a hard boundary between engineered safety and statistical vulnerability. Key principles underpinning the application of individual risk criteria include expressing risk as a fatality frequency. IR is typically represented numerically, such as 1 in 1,000 per year, 10 minute risk, meaning a person has a 0.1% chance per year of a fatal incident occurring due to a specific activity or installation. These values allow for precise benchmarking and regulatory alignment. Defining clear thresholds for IR acceptability. Unacceptable zone. IR levels above a defined maximum, e.g. 1 in 1,000 per year, are categorically intolerable. Activities in this range must be redesigned or discontinued. ALARP zone. Intermediate risk levels, e.g. between 1 in 1,000 and 1 in 100,000 year, may be tolerable only if risk reduction to a lower level is impracticable or grossly disproportionate. This zone requires formal justification and documentation. Broadly acceptable zone. IR levels below thresholds such as 1 in 100,000 per year are typically considered acceptable, provided standard controls are in place and maintained. Differentiating between workers and the public. Workers, who are routinely exposed and trained, may be assigned different IR benchmarks than members of the public, who have no control over their exposure. Public exposure must be minimized with even greater conservatism, especially near pipelines, gas terminals, or flare stacks near populated areas. Establishing benchmarks for design. New facilities are typically required to meet stricter IR benchmarks than existing installations. This reflects both technological advancements and increased societal expectations. Designs must aim for significantly lower IR levels than legacy assets. Basing criteria on QRA and HSSE IAs. Quantitative risk assessment, QRA, and health, safety, and environmental impact assessments, HSSE IAs, provide the data required to calculate IR. These assessments incorporate failure rates, occupancy levels, proximity, and mitigation performance. Ensuring clarity and transparency in risk reporting, every IR assessment must include the population at risk, operators, maintenance crews, contractors, public, the risk source, equipment, process, operation, the controls in place, the calculated IR level, the justification for its acceptability. Embedding IR criteria in decision gateways. Risk-based decisions, such as proceeding with a layout, approving an operational plan, or accepting a design, must be contingent on IR compliance. Tolerability thresholds serve as a go-no-go filter in engineering and safety reviews. Avoiding misuse of aggregated risk. High individual risks cannot be hidden under low average group risks. One person exposed to unacceptable risk cannot be statistically absorbed into broader safe averages. IR demands a person-specific safety lens. Treating IR as a moral imperative. These thresholds are more than regulatory limits. They are ethical boundaries. They quantify respect for life and dignity by ensuring that no one is put at undue risk for the sake of cost or expediency. By embedding IR into project and operational risk assessments, organizations move beyond abstract safety concepts into personalized accountability. It ensures that every individual exposed to risk is accounted for, not just in spreadsheets, but in design, decision-making, and duty of care. When used effectively, individual risk criteria transform risk management from system safety into human safety, turning numbers into lives and policies into protection. Risk management principles and procedure. Societal risk, managing the consequences of multi-fatality scenarios in complex systems. While individual risk focuses on the safety of a single person, societal risk evaluates the potential for incidents that could impact groups of people simultaneously: employees, contractors, emergency responders, and even the public. In the oil and gas industry, where dense occupancy, hazardous processes, and shared infrastructure are common, societal risk becomes a crucial lens through which project viability and safety resilience are judged. Societal risk does not refer to public opinion or the perception of risk. Rather, It is a statistical measure of the likelihood and severity of incidents involving multiple fatalities, and it demands a higher level of scrutiny and planning due to the scale of potential consequence. Core principles guiding the assessment and management of societal risk include quantifying societal risk using FN curves. Societal risk is plotted using frequency number FN curves, where the x-axis represents the number of fatalities and the y-axis represents the frequency of events leading to that number of fatalities per year. This visual representation helps stakeholders understand not just how often incidents may occur, but how bad they could be when they do. Setting thresholds for acceptability. Much like individual risk criteria, a societal risk is evaluated against defined boundaries. Unacceptable region. Scenarios that could lead to large-scale loss of life at frequencies above set limits fall in this zone. These risks require redesign, relocation, or other fundamental interventions. ALARP region. Intermediate scenarios may be tolerable only if further mitigation is proven to be impractical or disproportionate. Here, a detailed justification process must be applied. Broadly acceptable region, where the frequency and consequence are low enough that further action is not required beyond standard good practice. Applicability to fixed installations and densely populated sites. Societal risk assessments are especially relevant for offshore plants, gas terminals, refineries, and petrochemical complexes, where simultaneous exposure of many individuals is inherent in the design and operation. Inclusive of workers and the public, societal risk accounts for all individuals potentially affected, not just on-site workers, but also those nearby, such as visitors, transport personnel, or residents adjacent to pipelines and processing zones. Scenario-based evaluation. Societal risk is typically driven by specific high-impact scenarios: major fire, toxic gas release, explosion, structural collapse. Each scenario must be assessed for number of people exposed, event likelihood, escalation potential, mitigation effectiveness, e.g., evacuation, isolation, shutdown systems. Use in QRA reporting and design decisions. Societal risk outputs from QRA studies directly influence key design decisions: facility spacing, blast wall dimensions, evacuation capacity, muster area design, and personnel accommodation. It also informs emergency response planning and resource allocation. Avoiding risk aggregation errors. Projects must not mask high societal risks by averaging them out across longer timelines or broader regions. A rare event that could kill many people, even once in 10,000 years, is still often intolerable, especially when mitigation is possible. Supporting justifiable ALARP demonstrations. When societal risks fall in the ALARP zone, design teams must demonstrate that all reasonable and practical risk reduction measures have been considered, such as occupancy reduction, relocation of critical infrastructure, or engineering up. Public confidence and regulatory compliance. Managing societal risk is also about trust. Communities, authorities, and stakeholders expect that the worst-case scenarios are known, planned for, and reduced as far as possible. Transparent societal risk assessments reinforce the social license to operate. Ultimately, societal risk is the metric of collective responsibility. It ensures that projects do not just protect the individual, but anticipate, contain, and control the potential for large-scale loss. By embedding societal risk into the design ethos, organizations acknowledge a vital truth. In high-hazard industries, it's not only what we build, but how safely we build it for everyone who could be affected. That defines engineering excellence.